Let's start the new article 1.5 Center of Mass of a Rigid Body. But before we move further, let us clear some doubts about this rigid body because it is a new word for you. So, what is a rigid body? It is nothing but a system of particles in which the relative position of particles remain unchanged or invariant is called a rigid body. So this is the body of which kind? Rigid means a stationary type, means the particles. A position is fixed will not change further, which means that suppose here is one body, here is another body, and suppose this is body number 1 and this is the body number 2. Suppose this body is lying over here. Then what happens? Then the relative position of particles will not change, but this whole body will make some movement after lying the first body on it. So such kind of body is called a rigid body. Now there is an existence of a center of mass. In rigid body. So we can move further now to study about the center of mass in the case of rigid body. So first of all our task is to find out the location of center of mass. So here the location of center of mass depends on, see this is only relative to a rigid body and that depends on the distribution of mass in the body and also important shape of the body. We will also see the actual location of center of mass in different symmetries type of bodies. But first of all, we will see one more important parameter, that the center of mass can lie inside or outside the body. Or outside the body. So these are some characteristics for center of mass in a rigid body. So let us try to define the actual location of center of mass in different figures. So let's consider some symmetric bodies and try to find out the actual location of center of mass of the body. So here I am giving you some figures. So this is the first symmetric body in which the center of mass is, you can clearly see from the figure, it is inside of the body. Similarly, if you see in this symmetric body, it is nothing but a triangle in which the center is also at inside the body. This is the circle, and here the actual center of the circle is the same as the center of mass. Here also if you see this rod, then it is also inside the body, and here it is called a ellipse in which the center of mass is also inside the body. So these centers of geometrical figures are called the geometrical centers. And they can only exist into symmetrical type of bodies. Now the center of mass of a rod, consider this rod with uniform cross section, is also lying at its geometrical center, and these are experimentally defined or determined center of masses, but the center of mass can be obtained theoretically. So, which kind of process we have to follow for theoretical derivation of center of mass? So that is the sub-article of 1.5, and that is 1.5.1, theoretical method for estimation of the center of mass of the body. So we will see it on our next class. As we have discussed in the previous article, that there is existence of one theoretical method from which we can determine center of mass of a rigid body. But here the article says that center of mass of a solid body. So here the solid body which they have considered is nothing but one type of rigid body. But let us gather some information about a solid body. So any solid body is made up of a microscopic particle like molecules, atoms, ions, etc. These molecules are distributed continuously inside the body. So this is one characteristic about a solid body. Now, in the following figure which I am going to draw, I am considering a solid body. So in the figure, I have considered a small volume element dV. And this volume is containing mass dm. So this is the small amount of mass, and this term is considered as mass element. So this is about mass element, and this mass element is having the position vector as mass element is. So this is the position vector. I can simply denoting it as R, as the figure you have seen was in 3 dimension, and I am also drawing the figure below. As you can see from the figure that there are 3 dimensions x, y and z, and suppose I am considering my solid is becoming of the small mass elements. dm1, dm2 up to so and so dmn, and also their position vectors. Each mass element is having its own position vector. So this is R1, this dm2 has R2, and this dmn has its own position vector Rn. Hence, according to the definition of position of center of mass of the body, is given by RCM is equals to dm1r1 plus dm2r2 plus so and so dmnrn. Whole term is divided by the sum of mass elements, that means dm1 plus dm2 plus so and so dmn. So this is the equation. Now I am simply writing this term as integration form. So my RCM will be, this is nothing but the position vector into mass element dm, and the denominator is the simple integration of mass element. So this is one important equation, but if you consider the denominator term integration dm, so is this a total mass of the solid body? And I am defining as capital M. So I can rewrite this equation in the form of, so I am giving this equation as number 1. Now if we represent the position vector R, and from that I can write one equation for RCM vector as XCM I cap plus YCM J cap plus ZCM K cap. So this is the value of RCM, and we have the value of small r, means position vector. So just substitute all these value in equation number 1. So what we will get? Therefore XCM I cap plus YCM J cap plus ZCM K cap is equal to, this 1 upon m is outside the integration, and inside the integration there is simply putting the value of r, and the mass element will remain as it is. Now what you have to do? You just have to compare the left hand side and the right hand side. Therefore so what we will get? We will get the center of mass in component form for position vector. So see here, XCM is equals to 1 upon m integration XDM. Similarly, for YCM is equals to 1 upon m integration YDM, and ZCM is equals to 1 upon m integration ZDM. So this is the center of mass which we can determine theoretically with this procedure. And we will also find out the center of mass of a solid by taking one illustration. But before that, we will find out center of mass of a solid body in particular structure. So here is the subarticle of 1.5 in which we have to find out the center of mass of a solid body which having uniform density. So this is the first condition, and the second condition is it should have specific geometrical shape. So one technique which is used To find out the center of mass in such kind of case is the symmetry of the body. So we can calculate or find out its center of mass, but first of all we have to see the symmetry of the body. Using the law of symmetry, we can prove that the center of mass of such bodies means these bodies are having uniform density and specific geometrical shape lies at one more important word, geometrical center, which we have already discussed by starting of this theory, and in this theory we are going to prove that. Now, here I am considering one illustration by taking a triangular and my task is to prove that the center of mass of such triangle lies at its geometrical center. So first of all I am considering my triangular as, so this is the figure in which we have to imagine that a triangular plate has been divided into parallel thin stripes, means according to Mn. These lines have been done of MQ and NR. Here this C is the center of mass, but at present we will not consider that. First of all, what we have to consider is two slides, or this triangular plate is having a parallel thin stripes to side Mn of the triangular. So the stripes are MQ and NR. So these are the stripes. Similarly, if we consider the triangular plate can be divided in two other forms like MP and PN, so two triangular will be formed, then the center of mass of the triangular shape will be lying at their intersection point, so at this point. And also if you consider by taking a simple method which is the theoretical one, so from that the center of mass will be at its geometrical center. So here C is the geometrical center. And so with this our article number 1.5 is completely over. So we will switch on to the last article of this chapter 1.6.